Oh, welcome back. Alright, so we'll see how evenings go. That break's probably a little bit longer than I want, but I also know getting up, using the restroom, the facilities restroom, and also just having a mental break is important on this. So we'll play with this. Email me if you need anything to change. Just a quick, Emily had asked about the tablet I was using. So let's see if I can get my camera to work. Right here, this is, so I've got, it's an old Viz tablet. The thing's about 10 years old. And it's neat. It does what it needs to do. And I use OBS streaming software. It's open source. I'm a big open source advocate, and it runs on my Linux machines, but it will also run on Windows and Macintosh, which lets me switch between different windows on the operating system fairly easily. I had never used it until last week, and it didn't take too long. It was not much of a read the manual type thing. All right, so let's get going. We're diving into section 7.3, and we're going to learn how to divide polynomials. But I want to show you why, because where this is going is important for us. And this is something I have mentioned a couple times, and the idea, and I'm just going to use, oh, actually, I'll do it like this. I'll do it a little more explicitly. If I have solutions to some problem, what happens, or what I call a solution, is they're the points where f of x equals 0. And whatever polynomial or function I have, I can arrange it so that I can have it equal to 0. So, for example, if I had the polynomial x squared minus 6x plus 4, and I wanted to find out when a particular value of it was 3, right? When does this thing equal 3? I can subtract 3 from both sides, and I now have this polynomial in terms of equaling 0. So getting our polynomial in the polynomial form equal to 0 is a matter of manipulation that comes out of the problems we have been doing. I'm gonna erase these up in the corner here. So when we say it equals 0, we're looking for the points where it crosses the x-axis, which in this case here, I'm going to say that we cross the x-axis at -4, 2, yeah, that's 1. We'll say that's 1, and 5. And so without knowing any of the data anywhere else on the graph, I can at least get the most general form of this polynomial because I have 3 solutions. X equals -4, x equals 1, and x equals 5. Now remember, when I was doing the quadratics, we said, hey, if I have 2 things multiplied by each other equals 0, then I know the one equals 0 and the other equals 0. And I know I went up in the board and said, hey, that's going to be the same if I have 3 things or if I have 4 things, on and on. If I have each of these equal to 0, I can look at these factors and I will have a solution for the factors. And so I can actually turn these into factors. If I add 4 to both sides here, I get x plus 4 equals 0. If I subtract 1 from both sides here, I get x minus 1 equals 0. And if I subtract 5 from both sides, I get x minus 5 equals 0. And so these are factors that multiply up to 0. And I will get a polynomial if I do this. In fact, let's look at this polynomial because we want to see some information from it. So I'm going to do my FOIL here. So my first times my first is x squared. My outer gives me negative 1x. My inner gives me 4x. And my last gives me negative 4. I'm gonna scroll up from the graph so I have some room to put this polynomial here. I hope we get the idea that I'm looking for solutions or places where this has crossed the x-axis. So I will gather like terms. And I'll do my last division. And what I'm going to do is I'm going to multiply everything by x. And then I'm going to multiply everything by negative 5. And again, sorry, I got myself a huge glass of lemonade and I swallowed it down the wrong way. You can hear me cough for a bit here. I'm going to gather like terms. So x cubed is the only cubic term, but I have a 3x squared and a minus 5x squared, so that's minus 2x squared. I have a minus 4x and a minus 15x, so that's negative 19x plus 20. And so here I have a third degree polynomial that has the solutions I want. And let me come over here. What I really want to get is my dual monitor set up working so that I don't have to not see screens when I switch over. So like right now I'm switching over to Desmos to graph this, and I cannot see the numbers quite yet, so I have to switch back and forth, and this takes a little bit longer than I want, but that's okay. We'll get there. So negative 2, negative 19, 20. Negative 2, negative 19, 20. Negative 2, negative 19, 20. Oh, positive 20 was positive 20. My bad. Alright, I'm putting this into Desmos here, and I'll show you in a second. If I switch over to Desmos. Oops. It's here is Desmos. And notice that I got the roots that I wanted. Negative 4, 1, and 5. Now, there is an arbitrary constant that can go in the front of this, depending on where the other data points are. I can multiply it by some number. I still get the same roots, but this number out in front determines where my turning points are. And that's a lot of what we're going to explore, is how these polynomial functions relate back to the roots, and how we can go backwards from having the polynomial to finding the roots. And so what I'm trying to explore here in seeing this function and how this function has the solutions that I'm looking for. Go back to the blackboard for you here. Is if I start with this, I would like to find a process to find these roots. And if this is multiplying, if we need to go in a reverse direction of a multiplication, we have to divide. And so the thing we really want to explore with polynomials right now is we want to learn how to divide polynomials. So I can start with something like this and end up with these linear terms, these little bits of lines, so that I can find my solutions or roots. And we'll get a lot. There's a lot more behavior we'll see as we analyze what these functions do. But our first goal is, well, how do I divide this? Well, how does this thing work? And so we're going to look at it in two different ways. We're going to look at what it means to divide a polynomial by a monomial, and we're going to look at what it means to divide a polynomial by other binomials, which are the x plus 4s. And then we're going to be able to divide polynomials by any polynomials. So when we were building up multiplications of these things, we were able to multiply polynomials by monomials, and we were able to multiply binomials by binomials, and we're able to multiply larger terms by larger terms. So our ability to divide should do the same thing then. And we should process backwards. So the first thing we want to look at is we want to look at monomials and, whoops, sorry here, I'm trying to get up a note here and it's not showing up on the screen. There we go, there's that. All right. Let me try to switch here. My apologies, that was not clearing off. All right. So what I mean by a binomial, a polynomial by a monomial. So monomial has only one term. Now that term can be complicated. It can have multiple variables. It can have the variable to different powers and a coefficient in front, but it only has one term. And what we're going to use is we're going to use our friend from fractions, because fractions represent division. If we had the same denominator, we were able to combine the numerators over the same denominator. Now this came from all our properties of real numbers, right? What I could do is if I start with this, I could say, hey, this is a division. Well, division is the same as multiplication by the inverse. Okay. So that was our definition of division. And then I said, hey, I'm multiplying by the same thing, so I can pull that out front, because that is our distribution property. And if I have 1 over c times this, well, this is one number, so it would sit up there, and that's multiplying. And so this common denominator, if we have the common denominator, being able to write our function in one, or our fraction in one term, came from these properties of real numbers that we've been using the whole time. Well, again, anything we do in mathematics is bidirectional. If I start with this, I can end up here. But if I'm here, all the rules that make this happen let me reverse this. And so what we're going to do is we're going to use our division as if it was a fraction. And we're going to take the denominator and separate it across all the terms that we have. So let me pull up this fraction here. Scroll down. I'm going to turn off my neon green and I'll go with neon purple because I can. Alright, I'm trying to get my one window off to the side here. There we go. So I'm going to look at the division of 6x cubed minus 3x squared plus 2. And I'm going to divide it by a monomial, 2x squared. Now I'm going to write with the division sign here. You've noticed I have a tendency, I like to write my divisions as fractions. And I'm going to do this a little bit for now, just so because my emphasis is on the idea of dividing. But the first step I'm going to do is I'm going to write it in a fractional form. Now, this has three terms. These three terms could have come from a series of fractions sharing the same denominator. And so I have reversed my collecting of the fractions with the shared denominator. I have broken it apart, and because the denominator has only one term, I have put that below each term of the numerator. Please note, this is not reversible. I can't do this if I have terms down here. If I have 2x plus 1, I can't break the 2x plus 1 up by what's in the numerator. Right? The denominator is special here. And so this only works for breaking it across by the denominator. Well, we're not quite done yet. All right, we have the ability to simplify this stuff now. Because each of these terms we can treat as individual things. So I'm going to come over here. 6x cubed, I'll just rewrite this line down here. 2x squared, yeah. I'll actually point to it, and then I'll bring it down. So we're going to bring our answers down. So 6 divided by 2, right? Look at this fractionally, is 3. X cubed over x squared is x. 3 over 2 with a negative sign in front is 3 halves. And x squared over x squared is 1. The 2's cancel out here, and I get 1 over x squared. So I've simplified each of my terms. Well, let's check this, right? This is a division. It's reversible. Well, what did I mean by division? Well, I said if I divide this by this, I get that. All right? Well, if I divide 6 by 3, I get 2. And 2 times 3 gives me 6. So this times 2x squared should give me this. So let's check. All right, so we're checking here. So this will multiply by the first term. 2 times 3 is 6, and x times x squared is x cubed. 2 times negative 3 halves, well, the 2's will cancel, leaving with negative 3. And then negative 3 x squared. So bring each term across. Now the x squared, if I bring 2 times x squared times 1 over x squared, the x squareds cancel. That leaves me with plus 2. And that's what I started with. So this is a reversible process. I can multiply, and I can divide back out to reverse the process of multiplication. And it works with polynomials. Polynomials are able to be divided. The monomial part is nice because I break them into individual terms of fractions, and then I can focus on each term as an individual thing. And so in the homework, you'll be practicing the monomials. The monomials are a really nice practice. But I think our bread and butter, what's going to give us the most solutions, are going to be if we can divide by things that have more than one term. In fact, we're going to look at what happens when I have 5 x cubed plus, or whoops, minus 4x squared plus 7x minus 2. So I'll put all of that there. Do not know why I have the word connector hanging out there. I hope it's not showing up on your thing. Yeah, that connector is floating out there. Pop-up window came from somewhere. I will try to pop it back down. Ah, got it. Alright, and I'm going to divide this polynomial by x squared plus 1. A binomial. Now, we're going to borrow the algorithm from long division of numbers. And what we're going to do is, there's about 7 steps here. So I'm going to write the 7 steps, and then we're going to repeat this problem and come down. And it will show where it is. Now, there are things that are going to happen here. We might have possibilities for remainders. We might have different things that come out. But we're going to work on a repeating pattern that we can use for this. And so the first thing is, we divide the leading terms by each other. And we write this answer on top. Now I'll show all of these in long division. I'm going to write the steps down. I'm going to keep referring to these steps coming across. We multiply the answer by the divisor, and we write this answer below. Subtract. Bring down the other terms. And this is our new leading term. And so we repeat. All right, so I'm going to do this in two steps. Now, the thing that we're going to borrow from division of numbers, so try to write these down, have these off somewhere on a paper, and look at these steps 1, 2, 3, 4, 5, 6, 7, 8. I know you have a video. I know you can rewind me. I know you can make me repeat this. And I know I'm probably going to be embarrassed by this repetition for the rest of my life. But I'll get over it. But I think you should write down these 8 steps and have them kind of as a reference for when we look here. So this is the division I'm going to look at, but I'm going to take a short little detour, and I'm going to look at the division. Let me see. Yeah, I'll try to do it here. Of 36 is dividing into 5,483. I have no clue how close these numbers are. And what we're going to do is we're going to look at how place value determines what we can do. And so 36 cannot divide into 5, but 36 can go into 54 once. What I'm actually saying is 100 times 36 goes into 5,483, because my place value of this 1 is 100, but I'm just focusing on the place values individually. And so 1 times 36, so notice I did my leading term division. I wrote my answer on top. I multiplied. I wrote that below. And now I subtract. And so what is that? 18. And and I bring down the rest of my terms. So let's see, 54 minus 36 is indeed 18. And so how many times does 36 go into 188? Well, 5. Right? This is my new leading term, and I'm repeating. So I divide, I get 5, I write the answer on top. I multiply, which is 0, carry my 3. I subtract, and bring down my other term. And 36 goes into 83 twice. 72, I get 11. I have a remainder of 11, and so I can write that as 11/36. And so my answer of 36, 5,483 divided by 36 is 152 and 11/36. But the algorithm that we set up here and place value lets me determine this. We're going to borrow this algorithm and this idea of place for polynomials. And so we're going to look at place being the power of the variable. So I'm going to write my number down here. Here. I want to get this on the screen. I'm going to erase my long division here, and I'm going to start here where I can see this, at least for the first couple of terms, because I want to go back to those steps. I want to keep going back to those steps. Oops. Let's get that as an eraser. That's better. Almost looks like my eraser from class. And yes, I am missing my chalk. Alright, ink. Alright, so 5x cubed minus 4x squared. 5x cubed minus 4x squared plus 7x minus 2 divided by x squared plus 1. Yep, all right. So I'll put it here. So when I'm talking about leading terms, I am talking about the first term in the divisor and the dividend. So this is the leading term that's going to divide into this. So the first division I'm going to look at is going to be 5x cubed over x squared. I'm going to divide my leading terms by each other. Here's the leading term of this polynomial, and here's the leading term of this polynomial. Well, that's going to leave me a 5 upstairs, and x cubed divided by x squared is 1 x to the first. So 5x is my answer. So write this answer on top, and I'm going to line it up with my x to the firsts. Alright, so I divide the leading terms. Did that over here. I'll write this answer on top. Now I want to multiply this answer by the divisor. So 5x times x squared is 5x cubed, and 5x times 1 is positive 5x. And we write this answer below, which is what I did here. Now we're going to subtract. Now I am going to subtract by changing my signs. And luckily for me, I have so many different colors here, I'm just going to change the color so I know which sign I have. So that becomes negative 5x cubed, and that becomes negative 5x. Now notice, if I've done this right, if I've followed my algorithm, these will cancel. Right? And this can tell me if I'm doing my things right. These can cancel, and they do. Now I'm going to scroll up a bit, so we're going to remember these 8 steps because we're going to want to repeat. So these cancel, and this comes down as a positive 2x. This comes down as a negative 4x squared. Right. And I need to bring down my negative 2. So I subtract, I get negative 4x squared plus 2x. I bring down my other terms. And this is our new leading term. So now I repeat. I take negative 4x squared and I divide it by x squared. The x squareds cancel and I get negative 4. So negative 4 is going to go up here. I multiply this across the divisor. So negative 4 times x squared is negative 4x squared. Negative 4 times 1 is negative 4. I'm going to subtract. And so for me subtracting, I change the signs of this lower term. If I did my job right, the first term cancels. And it does. And so I get a positive 2x and a positive 2, which is my remainder. I can write my remainder. Remainder as the remainder over the divisor. And this is the result of my polynomial division. Ugly looking, isn't it? But we'll find it's useful, and we'll find some use for it. So let's look at some more divisions that we can have here and what we can do with these divisions. I want to do a couple of divisions. Let's check this one also first. Let's do the checking, as checking is important here. So I think I will, if this were to check, this times this answer should give me this. So x squared plus 1 times 5x minus 4 plus 2x plus 1 over x squared plus 1. That'll be my check. Alright, so x squared, I'm going to take x squared plus 1 and I'm going to take the whole thing and I'm going to bucket it into each term. So it's going to go there. It's going to go there. And it's going to go there. So, doing the first multiplication, x squared plus 1 times 5x I'll write the 5x out front. Right? We tend to like our number out front, right? So I'll do 5x times x squared plus 1. Isn't it nice that our multiplications are commutative, right? So they can commute. It doesn't matter the direction we go through. So, and I'm doing this just so I can keep my signs in a nice place. So the negative 4 times the x squared plus 1. And then I'm going to take this whole thing, 2x plus 1 over x squared plus 1 times my x squared plus 1. And so I've distributed my x squared plus 1. I'm going to scroll up a bit here. I've distributed my x squared plus 1 to each term in here. So this multiplication gives me 5x cubed, right, plus 5x as I move this to each term. This gives me minus 4x squared minus 4 as I move that to each term. But these cancel. And that gives me 2x plus 1. That fraction on the end always looks so ugly, but it usually checks the easiest. All right, so I'm going to collect like terms. 5x cubed minus 4x squared plus 7x, right, there's those, minus 3. Whoops, did I miswrite something? Yes, I did. That's a 2. That should be a 2. That should be a 2. I miswrote it when I put it up there. Oops. And so that should be a 2. And so 2 and negative 4 gives me a minus 2. And that's better. See, this is why we should check our things, right? We can find our small little typos. At least I had it right down here in my reminder. I just didn't write it up here properly. And it checks. And our work checks. All right. So this algorithm, this divide by the leading terms, write the answer on top, multiply back through the whole divisor. Notice we just do the leading term, and then we multiply by the whole thing. Subtract. Collect your new terms. You have a new leading term, repeat until you run out of leading terms. And this works for polynomial divisions. All right. Scroll to some clean board space here. And we're going to want to look at some different polynomial divisions. So I'm going to do one more, and I'll pull one from the book here. Let's see. I'm going to go into the stuff from the pen material on the book, and here we go. So we're going to look at x to the 4th minus 3x cubed minus x plus 3, and I'm going to divide it by x minus 3. Now, a couple things I wanted to note and why I chose this one, or why I was looking for one like this in particular, is I need to write this in descending terms of x, descending powers of x, to hold place. But notice I'm missing an x squared. So I need to make sure I hold that place. Just like 601, we put a 0 in to hold the tens place. In this polynomial, I have to put a 0x squared in to hold that place. But on the divisor, that's not as important. So in the dividend part, we definitely want each x power represented. But in the divisor, it's okay to not have them in order. So notice when I did the x squared plus 1, I didn't put x squared plus 0x plus 1. Your book in their example do put the 0x in there. I find that it's important, it's most important to have it here. In this dividend, you need to make sure that you keep track of each power of x. Over here, if you don't, you catch up over here because you're going to line everything up over here. Well, let's work this one out. So we start with our leading powers of x, or my leading terms of x. So the leading term here is x4, x to the 4th. My leading term here is x. And so I need an x cubed. So I put x cubed over here. And I'm going to multiply it back across by this. So x cubed times x is x to the 4th. And x cubed times negative 3 is negative 3x cubed. Now I'm going to subtract. When I subtract, I change the signs. I will change color for changing the signs. And if I've done my job right, this first leading term will go away. And it does. In fact, both of these terms go away, and I'm just left with a 0 over here. So I need to bring down the rest of my terms. Well, the only thing I have left is negative x plus 3. Right? These have all given me zeros. But I did my job right. This leading term went away. That's my check. All right. Well, this is my new leading term, so I have negative x. And my leading term here is still x. So I do this division and I get a negative 1. And so now I'm going to multiply this across by that. Negative 1 times x is negative x. Negative 1 times 3 is positive 3. And I subtract. So by subtracting, I'm going to change my signs. There we go. So I change my signs. These cancel out, and these cancel out. I have a remainder of 0. And so in this case, x minus 3 gives me the answer of x cubed minus 1. Well, let's check. If I multiply my firsts, I get x to the 4th. If I multiply my outers, I get negative x. If I multiply my inners, I get negative 3x cubed. And if I multiply my lasts, I get positive 3. If I rearrange this in descending order, hey, I got what I started with. And so my algorithm for division works. I can divide my way back out from where I started. And so we're able to do our long polynomial division coming across. All right. Well, polynomial division, again, we're working our way to finding the factors. And we get a form for polynomials. And I'll pull this out here. Any polynomial function of x, any, can be written as another polynomial times another polynomial plus some remainder. If the degree of d of x is greater than 0, and the degree of d of x is less than the degree of f of x. This doesn't look like it's going to do much for us, right? But it becomes very, very powerful. It lets us really talk about, well, I can talk about if I have, let me change color here to separate this from, this is our definition. Let's look at it as I have a dividend over a divisor. And that gives me an answer that we called a quotient plus my remainder over my divisor. Let's look at this. I'm going to scroll back up here. All the way up to, where is the number I wanted? Here. Here's my divisor. Here's my quotient. And there's my remainder over my divisor. Well, if I treat this as a very ad hoc equation, I can multiply both sides by divisor. So I multiply both sides by the divisor. I get the quotient times the divisor plus the remainder. And that's what this is saying. This is saying the divisor times the quotient plus the remainder. That's why they chose these names for the variables. These say the same things. But sometimes you start with this and you need to get these. Other times you have these and you need to get back over to here. And so recognizing these forms become important. All right. What I'm going to do is I'm going to look at one thing in particular that's going to lead us up towards working with finding roots and finding solutions, which is where we're going to spend most of Chapter 4. We're going to do some more division using something called synthetic division for the beginning of the next class. We'll start next week doing synthetic division. But right now, what I want to look at is one of the most useful parts of division, which is it's called the remainder theorem. And it talks about what happens to the remainder of a function. So I need to clean this off. So give me a second to clean here. Alright, and that should give a clean blackboard. Alright, so what we're going to do is look at the remainder theorem. And the remainder theorem says if a polynomial f of x is divided by x minus k, the remainder is f of k. Notice this. X minus k is a factor. In fact, it's a factor that we can look at, hey, k could be a root or a zero, this thing we're working towards using. Now, this doesn't tell us the answer of the division, but it does tell us if it has a remainder or not. And here's how we can look at it. So we're gonna do 2, maybe 3 of these, and we're going to do them both long division and using the remainder theorem to make sure it works for us. So the first one I'm going to look at as an example is I'm going to look at f of x equal to 5x squared minus 3x plus 1. And I'm going to divide it by x minus 1. So if we divide it by x minus 1, and all I want to know, all I want is r of x, the remainder. So I'm going to use my remainder theorem. I'm going to say, hey, if I am dividing f of x by x minus 1, my remainder will be f of k. Now, notice the sign here. I will mess up signs on these quite often. But this sign is negative. This sign is negative. So this is saying my k is equal to a positive 1. Right? Like we had in the circles, right? The circles had that negative in front of them, and to make sure when we were pulling out the points to get our center, that we needed to make sure that we kept track of our signs. And we'll find, especially as we go into synthetic division, keeping track of our signs is very important for us. So, to find the remainder, I'm going to want the function of 1. So I'm going to put in, for each of my x's that aren't in Texas, 1. So 1 squared is 1. So that's going to give me 5 times 1 minus 3 times 1 plus 1, which is 5 minus 3 plus 1, or 3. And so this is telling me if I divide 5x squared minus 3x plus 1 by x minus 1, I get a remainder of 3. All right, let's verify this, right? You know, just trust me, right? This works. This is a good theorem. But this is one that's actually worth doing a few times, working out, seeing that it's consistent, because this will save us a lot of effort. Having the remainder theorem, being able to drop numbers into f of x and not have to do the full long division all the time can help us. So let's do this the hard way. All I want's the remainder. So 5x squared minus 3x plus 1, and I'm going to divide it by x minus 1. Now I'm going to use my algorithm. I'm going to look at my leading terms. And so 5x squared divided by x is 5x. I'm going to multiply this back across. So 5x times x is 5x squared. 5x times negative 1 is negative 5x. And I'm going to subtract. So I'll change my signs. If I did my job right, these leading terms should cancel, and 5x plus negative 3x is 2x. Bring down my other term. Now 2x divided by x is positive 2. I'm going to multiply my 2 back through. I get 2x minus 2. I'm going to subtract. So I'm going to change my signs. If I did my job right, these leading terms should cancel, and they do. And 1 plus 2 is 3. Hey, look, I have a remainder of 3. Well, it looks like the remainder theorem works there for me nicely. All right, let's look at a slightly more complicated example. And this is the one I messed up earlier in the previous class because I didn't watch my signs. And it was a good learning experience on that, to watch our signs. Hopefully, I can mess it up the same way again here and we can watch our signs. It won't happen. Trying to make mistakes on purpose never works. Alright, so I have negative x to the 4th plus 4x cubed minus x plus 3. And I want to find the remainder when I divide by x minus 3. And so my remainder theorem says that x minus k, if I put in f of k, I get the remainder. negative sign, negative sign. So what I'm looking for is f of 3. So I put in negative 3 to the 4th plus 4 times 3 cubed minus 3 plus 3. Well, this is all for my calculator, and I'm going to put it into my calculator as I have it there. I get negative parenthesis 3 parenthesis to the 4th plus 4 parenthesis 3 parenthesis cubed minus 3 plus 3 did I looks like I did something, typed something wrong in again. What did I put in wrong? Plus 4x. Oh, I did a multiplication instead of a subtraction. I did multiplied by negative 3 here. Let me fix this. There we go. Make sure I hit the right keys on the calculator. If you check with your calculator, you get a remainder of 27. Okay. Still going to verify it. We're going to do it the hard way. Right? We have a remainder of 27. So let's do this the hard way. Change colors again. Negative x to the 4th plus 4x cubed plus 0x squared. I need to keep track of my 0x squared there. Minus x plus 3. All divided by x minus 3. So looking at my leading term, negative x to the 4th divided by x is negative x cubed. So I'm going to multiply this back across. Negative x cubed times x is negative x to the 4th. Negative x cubed times negative 3 is positive 3x cubed. I'm going to change my signs to subtract. If I did my job right, the first term should cancel out. And these leave me x cubed. Right, 4x cubed minus 3x cubed is x cubed. I'll bring down my next terms. And I have my new leading term. X cubed divided by x is positive x squared. I'm going to multiply the x squared back across. X squared times x is x cubed. X squared times negative 3 is minus 3x squared. I'm going to subtract. So I'm going to change my signs. If I did my job right, these leading terms should cancel. And this gives me 3x squared. I'm going to bring down the rest of my terms. This is my new leading term. 3x squared divided by x is positive 3x. I'm going to multiply this back across. 3x times x is 3x squared. 3x times negative 3 is negative 9x. I'm going to subtract, so I'm going to change my signs. If I did my job right, these first terms should cancel. And positive 9x and negative x should give me 8x. And I bring down my last part. This is my new leading term. So 8x divided by x is 8, and I multiply. 8 times x is 8x, and 8 times negative 3 is negative 24. I'm going to change my signs to subtract. If I did my job right, the first term should cancel out. And 3 and 24 give me 27, and I have a remainder of 27. So the remainder theorem worked. and it worked a lot quicker. It's like, well, what's the use of a remainder? How can having the remainder help us? Well, what's really, really nice let's come down here, is if I have 15 divided by 4, 4 goes into 15 3 times, multiply across, and I get 3. And so I have 3/4. Right? So we can't really say 3 and 4 are factors of 15. But if I have 12 divided by 4, and it goes in 3 times, and I get 12 with a remainder of 0, right? But we never used to write our remainders of 0. We're like, hey, it's inevitably, we're done. But my remainder was 0. Well, 3 and 4 were my factors of 12. So, if I have a polynomial and I have some clue of what might be one of the roots to it, I might be able to find out if it's a root without having to guess. And one of the things we're going to develop is we're going to develop ways of finding numbers that should be our roots for a large polynomial. So what I'm going to do here is I'm going to look at a polynomial, x to the 4th, so we'll say f of x is equal to x to the 4th minus 3x squared. Make sure I get the right, or 3x cubed, sorry. So I want to make sure I get the right one here. Minus 4x squared plus 12x. And for some reason, and we will find ways of doing this, for some reason I think that the number 2 is a root. I think that if I look at this 4th degree polynomial, it's going to cross the x-axis, and it's going to cross the x-axis there, and it's going to cross the x-axis at 2. It's going to cross at 0 and 2. I think they're going to be roots. And there might be other numbers that might be roots, but I have something that's telling me these are a definite possibility. Right? Well, how can I check without dividing everything? Well, if 2 is a root, x equals 2, then x minus 2 is a factor. And this should be divisible by x minus 2. It should be evenly divisible with no remainder. So it's telling me if I think 2 is a root, well then if I put 2 into the function, whoops, I have to put 2 in. So 2 to the 4th minus 3 times 2 cubed minus 4 times 2 squared plus 12 times 2. All right, so let's see. This is 16 minus, that's 8/24, minus 16 plus 24. Well, that cancels that cancels that, and I've got 0. This is the beauty of the remainder theorem. The remainder theorem will help us take the possible roots we have. Right? We're not going to be able to get exactly what the roots are, but we'll have possible roots. And it will quickly let us find the ones that are, so that we don't have to keep doing any other work, or we don't have to do the long division for them. We can go, hey, the remainder is not 0, so it can't be a root. Oh, the remainder is 0. It is a root. And then we can divide to get a simpler thing to work with. So the remainder theorem becomes really, really important later on. The whole process of polynomial division is really, it's going to be underlying everything we do, which is why we're going to be doing homework for next week on polynomial division. I'll be talking more about polynomial division at the next class period, and we're going to keep kind of really honing in on this polynomial division so that we can use it to its fullest extent. All right, so if we were in class, I would probably be throwing a worksheet at you at some point in time. We'd be doing these out by hand. What I'm going to do is I'm putting all my worksheets up as like little quizzy type things, just so you can get the points for them on that part of the grade book. If we have any problems with that I will adjust. But the main thing is I've set up homework for next week that uses sections 1 through 3 in chapter 4. We will be talking about synthetic division next class period. And I guess the big thing that we'll want to think about is for the long division, like we just looked at today, the divisor, the thing I'm doing the dividing by. Can be any one of these forms. So I can take any other polynomial and I can divide it by these things. Right, we're dividing by the divisor. But for synthetic division, which I'll start with next time, it can only be x to the first power. It can only be this particular binomial. Coming through. Now there's some power in it. It does go a lot more quickly than long division, but there's some tricks with the signs that we have to watch. So I would hope that everyone kind of gets to the point where they have their exam ready for chapter 3, that you're in a comfortable place with the chapter 3 exam, and that you start looking at the homework for chapter 4. And get comfortable with the long division, so that when we dive into the synthetic, we can kind of go back and forth. I spent ages in my career as a mathematician / physicist of never ever doing synthetic division. I did everything by long division, mainly because of sign issues and trying to keep track of the signs. I have found in the last 5 years of teaching it that synthetic division is useful to do these things quickly. Now, is doing it quickly worth it? That's a question of what you end up doing with this. You will find that finding roots and finding answers and finding this division actually comes up a little more than you would think. And in general, being comfortable with both methods will help you. But as long as you're consistent and quality, if you're comfortable with long division, you'll always get where you need to go. Just might take, a minute longer. All right, that's all I have for tonight. This video will be posted up here. Please email me if you have any questions. I will work out particular examples. I'm kind of doing the word problems for chapter 3, and I'm going to be doing more examples. I will be posting in the playlist for both MAT 097 and MAT 162 examples of long division, and some examples that I didn't cover in here. And so I'll be doing them in short little bite-sized consumable bits. I'll also look at some of the applications and word problems in the chapter, especially around the extremas, and what to do there. I'm also trying to put some stuff up for Desmos, but I'm going to respond more to questions I get in email first and add things around the edges from that. So I will end this for tonight. Be safe, be well, and I will talk to you all soon. Email me any questions you have.